introduce today's speaker, Professor Satish Mulleti, and he will be speaking on new trends in high dynamic range analog to digital converters. Professor Satish received Bachelor of Engineering degree at the Electronics and Communication Engineering Department, Jalpaiguri Government Engineering College, India in 2005, and Masters of Engineering degree in EE in the Department of Electrical Engineering, IIT Kanpur, India in 2009. Subsequently, he worked as a researcher in the ISRO, India, and TCS Innovation Labs. In 2011, he joined the Spectrum Lab at the Department of EE, IASC for his PhD. From 2017 to 2021, he was a postdoctoral fellow with the Department of Electrical Engineering, Technion, Israel Institute of Technology, Mathematics and Computer Science, Weizmann Institute of Science, Israel. Currently, he is an assistant professor at IIT Bombay. Sorry. Currently, he is an assistant professor at IIT Bombay. His research interests include sampling theory, particularly finite rate of innovation of signal sampling, compressive sensing, machine learning, blind convolution, sparse array signal processing, and spectral estimation. Audience is encouraged to ask questions during at any point of the talk. For those who attending online, questions may be asked either by unmuting or speaking directly or typing them in the chat box from where they will be relayed to the professor. Thank you. Over to you, Professor.
Hello, everyone. Can you hear me? Fine. Okay. Thank you, Srinivas, for all the arrangements and the introductions. So we waited 5 more minutes. So let's start into the talk. Okay. So today, as you know, I will be talking about high dynamic range analog to digital converters. Like name itself suggests that we may be having a lot of hardware and all those things, but we won't. Okay. And if you think that there will be a lot of maths, we will not have any maths altogether. So just pay attention. I'll walk you through what are these new things and all, and hopefully you'll learn something new. Okay. So let's start with few things. So we all know that we live in a kind of analog world. So you have a lot of things around you. You know all these things. Are you all aware? So we capture a lot of signals. All the signals are analog in nature. What do you mean by analog here? Anyone? Yeah. Anything else? Continuous time or continuous in space. You have values for each and every time and space and all, right? Okay, so we have a lot of things captured in analog world, right? But we like to process everything digitally. Yes? So I have every digital computers and everything, right? And why do you want to do these things digitally rather than analog domain? Okay, I don't want to ask too many questions. Okay, so simple things, right? Storage is very simple. In digital domain, we can do better transmission, digital communication and all, you might have studied. We can have faster processing in digital systems. Then, of course, we can show that we can reduce power and, of course, cost and all those things, right? So all these advantages are there when we process our stuff digitally, although we live in an analog world. Okay, have you recognized this thing? Do you know what is this? What is it? What is it? CRT TV. Have you seen these kind of TVs? Okay, do you want to have these kind of TVs or no, whatever flat screen TVs, smart TVs you have now? Of course, we want to have smart TVs, right? Not these. And we also have few magnetic tapes and all. I don't know whether you have seen those things or not. All those things are analog in nature. They process analog signals, show analog stuff. But we are moving back to digital, okay? And of course, I talked about two different worlds. Everything is an analog domain. We want to process everything digitally. How do we do that? We use analog to digital converters, okay? So the application, what I've shown, do we use them every day? Do you use your cell phone every day? Do you leave it? No, right? It's capturing all the analog signals, and of course, you are processing everything digitally. So there are ADCs there, okay? And there are many more sensors. If you go to hospital, we have different machines and all, which capture analog signal like ultrasound, ECG and all, but we process them digitally. And of course, now we are talking about autonomous driving systems, cars and all. They have several sensors which measures things around, which are all again analog in nature, and we want to process everything digitally. So whenever we have analog signals and digital processing, ADCs are there. That means they are almost everywhere. And they are very important building block and kind of a bridge between these two worlds. Is that fine? Okay. How many of you know already how ADCs work? Everybody? What are the two important things in ADC in terms of its working principle? Okay, sampling and First we do sampling and then what do we do? Quantization. Okay, let's talk about sampling. What is in generally sampling? Okay, so that is the first block. So there are two things, sampling and quantization. Let's talk about sampling. So here a signal which is f of t, t is time here. So this is analog signal, is it? Okay, now what do you mean by sampling? Yes, discretization in what? Time. So instead of having this entire signal everywhere, we measure it typically at uniform rate. Okay, every TS interval we take its value and those values are stored or represented as f of nTS, where here n is integer. Okay, we are going from time minus infinity to infinity, everything. On paper, theory, everything is possible. Yes, fine. So this is the sampling. And if I want to show it simply, okay, there is something wrong here. Okay, want to show it, sorry. Okay, so there is a kind of a switch which is closing every TS seconds, and then you are getting your samples. That's fine. Okay, it can close its switch at a slower rate or faster rate, all depends on your signals. Okay, at what rate should we close this switch? Nyquist? Everybody knows Nyquist? Is it only Nyquist or something else is also there? Shannon? Okay, whether it's Nyquist or Shannon? Shannon or Nyquist? Shannon, Nyquist both? Okay, so different parts of the world, different names are there. Okay, so if you look at, like we know Shannon, but the paper which talks about all these things came only in 1949. So few of the early works were also there in 1915, 1928 and all those. Okay, you go to Britain, people talk about Shannon, Nyquist and Whittaker sampling theorem. Okay, and if you go to Russia, they talk about only Kotelnikov sampling theorem. And Japan also has some guy who talks about this sampling theorem and all. They have their own sampling theorem. Okay, but what we call it Shannon-Nyquist sampling theorem and all, and what it says generally. Okay, this is a standard PhD interview question that we ask to every student. Okay, you have a signal which is, we typically say that band limited. That means it has a highest frequency component, and you take your uniform samples at a higher rate. If the high frequency, more samples and all, then you can get back your analog signal from those samples. That is a standard sampling theorem, right? Okay, is the sampling good enough? So can we do after sampling all the digital processing and everything? Or should we do something more? Quantization. Okay, why should we do quantization? All those samples that I showed have still high precision. Here, what do you mean by high precision? They can take any values, right? Of course, I cannot store them in any terms of bits or finite things and all, right? So I need to do some sort of a quantization. Okay, let's talk a little more about quantization because we will be using those concepts more. Okay, so here is my analog signal and there's corresponding samples. So each of these samples can take any of those values. That's fine. Okay, what do we do for quantization first? We divide everything into some number of levels. Fine. What are these levels called? These levels are typically called decision boundaries. Okay, and within each level, we have something called representation levels. Okay, and after this, we do our quantization. What is the rule here? Is that if your sample or signal is falling in one of these levels, between that, then you pick something, you represent all the samples by this value, right? For example, I can do this. So are falling within this level, these four samples are represented by this level. Similarly, I can do everywhere. Is that fine? We have all done this kind of things earlier. Okay, fine. So quantization is performed, and now the sample signal is quantized in both time as well as in terms of amplitude. And you can store everything on a digital system. Is that fine? Now, a few important things when we talk about sampling. Okay, this one. What is this called? Generally, do you have any new term than what I know? Step size. Okay, so typically we call it step size, but people may have different names and all. What it should be? Should it be small or big? Small. Why? Huh? Better precision. So if it is smaller, see, for example, if I have this particular sample, I'm representing this by this, and largest error I can have is delta by 2, right? I'm losing my information when I'm doing quantization. When sampling and sampling above Nyquist rate, I won't lose any information. But while performing quantization, I'll lose some amount of information. And if you don't want to lose more information, delta should be as small as possible. Is that fine? Okay. So the rule is that smaller delta, smaller error. Fine, we want to have smaller delta. But what are the drawbacks for smaller delta? So if I make small delta, I need to have more number of levels and I have to have more number of bits. So your bit rate will increase, right? So example, let's say you are in a network where the speed is not huge. So can you download all those high precision videos and all? Of course you cannot. So that's a big problem, right? So while having these quantization all, there is always this trade-off, high number of bits or higher data rate and all those things, but it all depends on application and what you want. But please remember this term, we'll come back to this later. Okay, fine. So one more interesting thing. So we talked about sampling rate. It should be greater than Nyquist and whatnot and all. Here, in terms of quantization, we said that, okay, number of bits should be as large as possible, okay, to reduce the error. That's fine. So few more important things that we never usually talk is signals dynamic range and ADC's dynamic range, which will be of point of interest in this particular talk. What is the dynamic range in general? Those who know, we can say that. What is dynamic range? Huh? Voltage? The largest to smallest. Okay, there is a signal can go up and come down. Let's say that is the largest is plus a volt, it's minus a volt. So dynamic range is 2a. Okay, and similarly, when we are doing quantization and all, we have some sort of a dynamic range. Okay, so what should be the relation between dynamic ranges? Louder. This should be larger than this, you're saying. Okay, otherwise what will happen? Okay, so the point is that ADC's dynamic range should be much larger than the signal's dynamic range. Otherwise, what will happen if your signal is very big? It will get clipped. That we all studied at one point of time. Okay, so let's try to understand dynamic range. As I say, dynamic range of the signal is, let's say, plus A to minus A, capital A, and then dynamic range of your ADC, like what is the maximum level it can accommodate, is plus lambda to minus lambda. Is that fine? Let's try to understand from three different scenarios the dynamic range issue. This is the first one. Okay, so here the signal's dynamic range is much larger than the ADC's dynamic range. Here we have quantization levels and all those things. So what's happening? All these samples that having the same value, essentially we say that they are clipped. You don't have that information at all. Fine. So what if your signal's dynamic range is very small compared to ADC's dynamic range? What will happen then? Will that be good? Why? Yeah, it might not detect. So for example, my signal's dynamic range is much smaller. So what will happen? All your variations will be buried under your quantizer's step size, and there won't be any variations in the signal. It looks pretty similar to what happened with clipping. Okay, you cannot detect any changes and everything. Fine. So ideal scenario will be something like this. So your signal should go through the entire dynamic range of your ADC. That's fine. So we have two scenarios which are undesirable and one desirable scenario. Now these are like some sort of images that I generated, not even using MATLAB, just for illustration purpose. But what it mean in real life? Okay, we all take pictures using mobile phones, right? Have you ever faced this dynamic range issue? Especially when there is a bright object and you're standing in front of it. Let's say I want to capture sunset as well as your face. Were you able to capture both? How many of you have tried that? Have you seen this issue? Like the sun behind and you're standing in like your back towards sun and you want to capture both. Nice sunset. If you focus on sun, you will lose your face. If you want to focus on your face, you will have bright sun. You won't see that nice ring. Yes? So that's second dynamic range issue. Okay? So here I want to show something using these three pictures. So here everything is clipped. You cannot see any sun. Okay. Here there is no variation. You can see like a patchy picture. I did a lot of attenuation here. And if you see, this is the ideal picture that I wanted to have. All are taken from mobile phone cameras, but I just changed the quantizations and all. Is that fine? So this is a more desired scenario and all. Okay. So we talked about sampling rate and all. It should be Nyquist or above Nyquist, everything is fine. Okay. We talked about number of bits. more the better, but depends on your application, of course. And we talked about dynamic range, and your ADC's dynamic range should be greater than, sufficiently, not sufficiently greater, but greater than your signal's dynamic range. Okay, those are the three things. Now, another important aspect I want to cover from next slide onwards is the power consumption. Okay, which is again very important. Okay, we talked about ADCs and everything. How many of you looked at the power consumption aspects of anything? Why should we worry about power consumption? Anyone, take a guess. Oh, something wrong? Right. Fine. Okay, so what will happen if we have power consumption issues? How many of you have this issue earlier? How many of you had these kind of issues earlier when you're connecting your laptop and all and you have power consumption issues? Because everything is using ADCs and all, you're draining your power out, right? From the batteries and everything. If you look at this scenario very carefully, nowadays you are having lot of those things that, again, that requires lot of battery power, okay? Especially in and around you. Look at these applications. How many of you have smartwatches with you? Of course, mobile phone, everybody. How many days the battery last? 10, 15 or less? 10, 15 based on use, right? You want to have more battery power, right? Of course, right? So we have a lot of wearable devices nowadays and everything operates on battery. Does your smartwatch has ADC? Okay, think about it. Possibly yes. Okay, then we have several of Internet of IoT thing sensors and all in and around us. Everything operates on battery. Are all sensing analog signals, and they have to convert them to digital signals and transmit for further processing. So we have ADCs there. Okay, and they consume some power. Okay, then we have several other things like how many of you see using these things or devices and all? Are they always on? Are they always on? Are they always used? Power is always connected, but they're not used always. Okay, they have to be always awake and keep hearing us. Okay, power consumption is important aspect there as well. Okay, then of course we have autonomous driving systems and their corresponding sensors and all, which will always be working on mostly battery power and all. So power consumption is important aspect in most of these kind of applications. Okay, and all these applications are typically measuring analog signals, fine, and they have to convert it to digital domain, and ADCs are there. So power consumption of ADCs is what we will be focusing on. There could be other devices and all connected to these things, which will also consume power, but our focus is on power of ADC. Is that fine? Okay, let's move forward. So let's understand how power of ADCs work. Okay, and why should we have low power ADCs? Now, low power ADC, that motivation is clear, right? All these devices are ADC, we want to have low power ADC. Okay, so three different aspects that we consider for an ADC are these three things. Fine, sampling rate, number of bits, dynamic range. How many of you done any power electronics, any such device courses? I also haven't done that. Okay, but I read a few papers, and what they said is that for ADC, the sampling rate increases, then the power consumption will increase. Okay, if you increase your number of bits, the power consumption will increase. How much will they increase? Okay, there is a nice relationship people have summarized this one. Okay, this is the first equation that we are showing right now. Okay, what is it saying? The power consumption of ADC is proportional to sampling rate. Higher the sampling rate, the power consumption will increase linearly if you are not increasing, changing anything else. Okay, here n is number of bits. So power consumption is also exponentially related to your number of bits. So keep on increasing number of bits. Let's say you're going from 6 bit to 7 bits, the power consumption will be twice compared to the previous one. Okay, that's very important. Earlier I said higher the number of bits, better it will be. But where are we losing the game? In terms of your battery power. You will be draining your battery more. Okay, these are fine. Okay, how about the third thing? Any guesses? Should it increase? Should it stay? Yes? How? Louder? Why? Okay, you are right, it should increase. Okay, with the dynamic range, everything should increase. But why is pretty simple. If we just go a little deeper, you'll understand. So whenever there is a high dynamic range ADC, we need more number of bits to have same error. But to keep few things constant, we cannot change everything, right? So let's say there is a two different dynamic range ADCs, but we want to keep the error same. So step size delta is same. So higher dynamic range, that means more number of bits. And whenever we have more number of bits, the power consumption will also increase. That's the relationship. So all these three quantities which we thought are very important for ADC's design and use and all, if you keep on increasing them, the power consumption will keep on increasing. Okay. Now here is a question that we are going to answer in this particular talk. Can we sample a high dynamic range signal? That means the dynamic range is very big. Okay. Typically, I need a same amount dynamic range ADC. But can we sample a high dynamic range signal with a low dynamic range ADC? If we say that yes, we can do that, then what is the, oh sorry, I'm pressing the wrong button every time. Yeah, advantages, we can use fewer bits because the dynamic range of ADC is very small. For the same error, we can have fewer bits. It will be memory efficient because you don't have too many bits. Okay, and of course, as I said, it will have lower power, hopefully, right? We are reducing the number of bits. Now, how about this answer? What could be the answer? I have a huge signal, but ADC's dynamic range is very small. What should we do? Simplest solution. Reduce its size by scaling it down. How many of you agree with him? Should we scale it down? Yes, no. There could be only one answer, right? Yes or no. Just pick something randomly. Should we scale it down so that it will fit into dynamic range of our ADC? No. Why? Oh, that's fine, right? But we are sampling and reconstructing. Okay, let's try his method. Okay, let's do the attenuation. Fine. So typically these are called attenuation, or in some literature it's also called automatic gain control. Those who have done communication courses and all, they might have heard this term, automatic gain control and everything. Yes, EC department, I suspect like most of you have heard this time. Fine. So what are we having? We have this huge dynamic range signal. Let's say ADC's dynamic range is only this much, small. He is saying that scale it down. Okay, so let's scale it down. So what's happening here? What are the big changes are there? They're still visible. We are able to capture them. However, whatever the small changes are there, they keep becoming smaller and smaller. Okay. After a certain point, if there is a huge variations in the signal, you cannot capture those small variations. They'll again buried under. You need to have more and more number of bits again. Okay. So it depends on what are the big range signals that you want to detect in the signal and what are the smallest possible thing that you want to detect in the signal. If that ratio is too big, even if you want to attenuate, then you may lose some information. Okay. Any questions? Is it fine? Okay. So this may not be always a feasible solution, attenuation and all, but people still use some other forms of attenuation and all, but may not be always feasible. You may lose some information in this process. Is that fine? So to address these things, people have come up with some alternate solutions. Okay. This is called unlimited sampling or modulo ADCs. Here unlimited means you can use any dynamic range signals and all. Okay. And one of the first early paper in this direction comes in 2017 and all by a group by Ayush Bhandari and all. And they are the leading guys who are working in this direction. And there are several other groups, okay, who will be working on this thing. So what is their main philosophy is that your signal has a huge dynamic range, ADC doesn't. Okay. Why not wrap your signal before you send it to your ADC so that you keep all the information? It'll be difficult to understand like that, but I just want to show some example here. The blue one is my high dynamic range signal. Is that fine? Okay. And plus lambda to minus lambda is my dynamic range of ADC. Okay, fine. So I'm just wrapping the signal using modulo operation. Okay, I'll just enlarge it so that you can see it better. That's fine. So I'm just folding it so that it always lies between plus lambda to minus lambda. Am I throwing away something here? Am I having all the information? Unlike clipping, where we are throwing away something, we are not clipping here. We are keeping almost all the information here. Is that fine? Okay. And this entire process is done through modulo operation. We all know what modulo is. Okay. What is 13 mod 2? 1. Fine. So similar modulo operation they are doing. Here, when I say 13 mod 2 or something mod A or lambda, everything lies between 0 to lambda. But here this is called centered modulo. That means everything will lie between plus lambda to minus lambda. That's the operation they are doing. And modulo is always instantaneous operation, memoryless. It will do point-wise folding. So that is what we have. Okay. Now, once we have this modulo operation, what we do is that we do sampling. So earlier we have original signal and the original samples which are shown in magenta. Let's say we are talking about sampling. Right now, I'm not talking about quantization at all. Okay, we are just talking about sampling. Okay. Now, instead of having this magenta samples, we have all the samples which are shown in black. Because I don't have original signal, I have folded version. And now I'm sampling the folded version. Is that fine? Let's try to understand this, because based on this, we'll move forward. If you have any questions, you can ask now. Okay. Just to clarify modulo operation once again, 5 mod 3 is 2, 12 mod 3 is 0. Okay. And instead of having 5 and 12, that is our original samples, let's say, we are having 2 and 0. Is that fine? Okay. And in terms of a block diagram of framework, what we are having this signal f of t. What are the signal which originally we wanted to sample? We are passing it through that modulo folding operation and just showing it through this operator. And we have this folded signal, which is shown in red here. Okay. What is the dynamic range of folded signal? Plus lambda to minus lambda, same as our ADC's dynamic range. Here I showed ADC, lambda is dynamic range, and TS is sampling. Now I have folded samples. Okay. Does it solve the problem? We said we want to sample a high dynamic range signal through a low dynamic range ADC. Does it solve the problem? Yes, no? No, why? Little louder. Fine. At least our problem, can we sample? Yes, we can sample. Okay. Now, another question, after sampling, can we do reconstruction? That's where the difficulty lies, as you suggested. Okay. We can sample. We are not throwing away any information. We did sampling and we got everything. Now, the question is that how to recover the original signal from the folded samples. So first question, can we recover the folded samples themselves? And if I have unfolded samples, clean samples like in magenta, I know that I can get back the original signal. Okay. And the question also is that should we sample higher than the Nyquist rate in this case, or should the Nyquist sampling should be good enough? Okay. That also we have to answer. Is it clear? So we are keeping all the information to us. Now the question is that all the information is now in a folded version. Can we get back everything? Is the question. Fine. So let's try to understand what people generally say. So if you look at all the theoretical results in this work, they say that if you sample slightly above the Nyquist, that should be good enough theoretically. Okay, when I say theoretically, let's say if I want to ask you to solve a linear set of equations, y is equal to ax. Okay, first question I should ask you is that, is the problem solvable? Okay, then what's the answer? You'll say some answers in terms of the conditions on A. Let's say A should have full rank, it should have full column rank and all those things. Okay, but you're still not telling me how to solve it. Right? The solution could be using Gauss elimination method, this, that, and all. That will come later. Whether we will be able to solve the problem or not, you first talk about that. So in that context, people talk about this is called identifiability. And they said whenever you have band limited signals, you can sample slightly above the Nyquist rate, and that should be good enough to get back original signal from the folded version. That's the theoretical guarantees. But in practical algorithms work slightly differently. So we'll talk about some practical algorithm, what usually they use. There will be different recipes, but we'll talk one simplest recipe. Okay, fine. Okay, we talked about these two samples, right? Fine. So our lambda is 3 here. I'm taking 0 to positive modulo only, just to see how the reconstruction is. Okay. What's given to us? We are given 2 and 0. And we want to understand whether it's 5 and 12. Fine. So let's look this as a some signal. So this is a linear signal, ft equal to t for simplicity. It's not band limited. I'm just giving an example. Is that fine? So the signal is sampled at 5 and 12. The values are 5 and 12. That's what we have. And we are folded those values using modulo version. This is a mod. So samples will fall somewhere 2 and 0. Is that fine? This is scenario. So how should we get back from 2 and 0 to other things? Any thoughts? So if I give you 2, what are the possible solutions? Don't look at the left-hand side because you don't have this. You only have this. If I give you 2, what are the possible solutions? Huh? Now, if you know 3, this is a folded by 3. Lambda is equal to 3. I given you 2. What are the possible solutions? 8, 5, and all those things. So keep on adding multiple of 3s to 5, and you'll get all those things will give you 2 only. Similarly for 12, 12, 15, 18, 21, everything. Okay, mod of that will be give you 0. Okay, so if I give you 2 and 0, of course you don't know what's happening. You need to have little more information. Okay, now let's say I have only 2 samples, right? One is at 5, one is at 12. What if I take more samples now? I'm sampling more. I'm giving more values here. Okay, let's start again. This is the same process what we had done. Okay, the first sample is 2. What is your solution? What could possibly be? First sample is 2. Then what could be the possible input? Give me one value, louder. First sample is 2, right? What can you guess? What could be the input, actual signal? 5 is anyway given. Let's guess something else. 8, fine. So 8 is my first sample. The second sample is now 0. What could be the next one? Next sample, guess. It could be 6 or anything else. Okay, now this is 6. Third is 1. What could be the possible solution? Guess something. 4. Fine. So these are the values, but these are not same as what we have, right? These are completely different. But now I'm doing oversampling, right? I'm giving you more samples. And I'm saying that the original signal from one sample to another sample, it's not changing drastically. Okay, so you have your first guess, which is 8. Okay, next guess cannot be 6 or anything. It should be pretty close to 8 because that's the assumption I have. So what should be the next guess? What should be the next one from 0, from 1? Okay, are we able to reconstruct the signal? Yes, no. What were the original values? 5, 6, 7, and you are getting 8, 9, 10. Is it still linear? Okay, just there is an offset. Yes, fine. So here the idea is that if you keep on oversampling, the one sample to another sample, the signal is not changing drastically. Agree? So let's say you have some signal like this. If you keep sampling like this is a general sampling, but let's say you are oversampling, densely sampling. So if you see from here to here, the change delta is very small. Okay, though I have folded sample, I can guess the first one, and for the next one onwards, I cannot go too far from what is the original guess is there. Okay, and with that, I can reconstruct the signal, but with some offset. I'll get to that. Okay, this is just a linear equation, right? Just want to explain what's the point. Is it clear? So that's the assumption what we have. Okay, we say that if we assume that the signal samples are not changing significantly from one sample to another sample, then there is a way we can get back the original samples from the folded one up to a constant factor. And constant is okay. In most of the signal processing application, we are fine with the constant. Fine? Please. We'll come to that. Good question. Just hold your thoughts. We'll come back to that. Okay. Precisely, that's what we will be discussing. Yeah. Any other questions? Okay. Fine. Fine. Yes, please. The noise and all those things. Yes, there are results for noise and everything. But even noise is always usually bounded, right? You cannot have unbounded noise. So you can always oversample. Even let's say this is riding with some noise. Let's say this is maximum deviation your noise can have. So can you always get some bounds? You may have to oversample more. Okay, fine. So what if I write a simple mathematical equation from this is not the folded sample, this is the original signal sample. So one sample to another sample, the difference should be bounded by lambda. What is lambda? That's like a plus minus lambda is my dynamic range of ADC. If that is true, very simple algorithms are there. With that, you can get back everything. Okay, is that fine? Everybody? Yes, please. I never said lambda will be very small. The difference between the samples could be very small. Lambda is fixed. I'm talking about the original signal that you are sampling. I have folded signal, but I can make an assumption on what kind of signals I'm dealing with, right? Let's say I'm dealing with all band limited signals with some energy and all. And I can make always this assumption that this is always satisfied. So input signal class is what I am dealing with, band limited signals or something like that. Earlier we talked about band limited signal, right? Something like that. Need not be band limited. There is a different way of dealing with that kind of things. So there are different set of results for those class of signals. Which signal? Huh? Let's okay, this is our here, this one. Yes. Red one. Yes. We are making assumptions on the blue one. We don't know blue one. We are just saying that blue is coming from a class, right? Let's say blue is band limited. Okay, let's say blue is band limited signal. Bandwidth is something. I'm not saying that what kind of signal it is. I'm just saying that all band limited signals. So can we make some assumption on if all band limited signals are there, I sample at certain rate above Nyquist, then one sample to another sample changes could be minimal. I'm not talking about a specific signal. I'm talking about a class of signals here. Okay, assumptions are done on blue, not on red. Is that fine? Is it clear? Okay, fine. Okay, let's move forward. Okay, so these are the first few papers that talked about these kind of reconstruction, but there are several such reconstruction exist much earlier in different contexts and all. So I talked about oversampling, right? Oversampling means how much above the Nyquist rate. Okay, so first few papers talked about the oversampling rate, which is 17 times the Nyquist rate. And they say that there will be guarantee that band limited signals are there. You can sample at this rate, and then you are guaranteed that you can reconstruct the signal from folded versions. Okay, we'll get back to your question, why should we do oversampling and all? We'll get back to that. But oversampling rate was this much. Okay, now let's talk about her question and a kind of a comparison. What if I use a ADC, which is having a full dynamic range? Okay, and what if I use a modulo folding and then ADC, which is a smaller dynamic range? What am I paying? Where am I gaining? Okay, this is just a question. This is still open questions are there. Okay, so I have this table. Okay, let's talk about the conventional ADC. what all we have? Its dynamic range is -A to A. Sampling rate could be greater than Nyquist, but for band limited signal, we know that we can sample at Nyquist rate for perfect reconstruction. That's fine, everyone. Okay. Now, number of bits is NA. Those many bits are there. So in both the ADCs, few things has to be common. So I'm assuming that the step size is fixed. Okay, fine. That means your total dynamic range divided by 2 to the power n should be constant. Fine. So what is the bit rate? Sampling rate into NA. This is fine, everyone. The bit rate is this. And then this is the power consumption. Like power consumption should be proportional to this. This factor is fine. We talked about this. Okay, just remove the power. Now comes to modulo ADC. Look at those numbers. So dynamic range is minus lambda to lambda. I said I'm sampling at oversampling factor into Nyquist. Okay. So because the number of dynamic range is small, I need a smaller number of bits. Okay, step size is same. So here the number of bits is n lambda, which could be smaller. So A is always much greater than lambda, right? A is the dynamic range of the signal. Lambda is the dynamic range of your ADC. Is that fine? So n lambda is smaller than NA. You can use fewer bits. That's fine. Okay, fine. Now in terms of bit rate, I gave all the numbers here. Fine. So these are the number of bits and this is the sampling rate. And similarly, I have a number for power consumption. Okay, both the things are on table. Let's try to do a fair comparison. Okay, here the quantization step size is same in both the cases. Is that fine? Okay. So let's look at this number. If I want to have the same bit rate, what should this thing should be? If I want to have a same bit rate in both the scenarios, should be 1. So let's say if the dynamic range of signal A is 10 times larger than lambda. Okay. So A is equal to 10 lambda. In that case, oversampling factor cannot be greater than 10. But we saw that in few cases, it is how much it is. Theoretically, it's 17 for most of the algorithms. So we need to bring it down. Okay. Then in terms of power consumption, are we saving in terms of power? See, number of bits we are reducing. Yes. So which one is related exponentially to the power consumption? Bits or sampling rate? Exponentially. The number of bits. Sampling rate is related linearly. Power consumption is proportional to the sampling rate and 2 to the power number of bits. The number of bits you are bringing down, so that will have a huge effect on your power consumption. Then how much you are increasing your oversampling factor. But if you still want to do a fair comparison, you have to equate these two things and find the oversampling factor that is optimal in both the cases. That means how much it should be. For example, here I said that oversampling factor into lambda by A should be equal to 1. So that is giving us a bound on how much oversampling factor should be there for the algorithm so that we don't lose out the advantages of these kind of ADCs. Is that fine? So even though we are oversampling, the advantage is that we are reducing the number of bits drastically, which will have a huge impact on power consumption because the bits are related exponentially with the power consumption, then linearly as in sampling rate. But still, it's a very fair and valid questions. In many cases, this may not be a fair comparison, the modulo ADC may not work directly. So we have to do something better. Yes. Yeah, tell me. Lambda is fixed, A is fixed. Oversampling factor, it depends on your algorithm. That is what we want to improve. That's as I said, theoretically, oversampling factor is equal to 1. Theoretically, great. Let's greater than 1. That should be good enough. Okay. But practically, few earlier papers talk about oversampling factor, which is 17 times. That's the only thing that we are playing here. Depends on what you are interested in. You cannot tick all the boxes in practice. Any of this. If I want to have a win in terms of bit rate, I want to say that, okay, power consumption, I don't care. I want to win in terms of bit rate. It should be lower bit rate and all. Then I have to focus more on making sure that this is 1. Then here I said that we have to equate both the things and find what should be the oversampling factor so that both are same or this is smaller than this quantity. Then I have to say that what is my upper limit on oversampling factor? How much should I reduce? Okay. Yes, please. We can keep on increasing. Okay, go ahead. A is a dynamic range of the signal. It's like fixed. How will you keep on increasing? You want to have another amplifier? Lambda A are fixed. All these quantities here, except for oversampling, are fixed. We can, with these equations, depends on whether we want to use bit rate constraints or power, we can keep those kind of oversampling factors. That's why one direction of research in this areas. So as I said, first paper was in 2017. Then there are several follow-up. So yeah, oversampling factor should be small. There are several follow-up works. First time paper, they said 17 times. Okay. Then there are several follow-up papers kept coming. They are all talking about how to reduce this oversampling factor from 17 times to which is something more feasible. So for example, last ICAS, there was a deep learning based paper and all, which says that, okay, 3 to 4 times oversampling will also work. But again, if you look at, remember that equation, it's lambda by A into F, right? So every time lambda by A matters. So higher the dynamic range of the signal compared to your ADC's dynamic range, you always need more oversampling. And we always ignore noise here. If there is more noise, we have to pay more oversampling and all. Then the power equations and everything will change accordingly. Okay, sorry. So people keep talking about more and more papers and all, which will talk about oversampling factors and everything. Of course, all those things, as I mentioned, can be proven theoretically on pen and paper. Then you can write MATLAB Python codes and show all the results and everything. But will it actually work in practice? So people also show that many of these works and all, where they say that you can actually build a hardware and show that these things will work. So when I was doing my postdoc, so this was my previous group and all, which we talk about this board that they designed. For example, if you see this sinusoid signal, which has a huge dynamic range compared to ADC, and they showed that how can you fold those signals and then of course reconstruct everything. So it's not only like people are much more interested nowadays in showing things in hardware and all, and show that, okay, whatever works in theory, it can also work in practice. Okay, fine. So now here we are doing oversampling, right? And what are we reducing in general? Number of bits, because the dynamic range is small and we're reducing the number of bits. So is this concept well known? Yes, please. Plus? Oh, I didn't get it. What do you mean? Do we know that? You can always have an upper bound. See, when people talk about unlimited sampling as theory, unlimited means A can be anything. Theoretically, there is no limit on A. Okay, but when it comes to practice, you have to have some limit. People have talked about different. A could be only 2 times lambda, and there are some different algorithms, but there is very restrictive. It could be something different. You can modify your algorithms accordingly. Yes, that's possible. Okay. So this oversampling and reducing the number of bits, is it a well-known concept? Or people talking about completely new here? How many of you have done this already? How many of you have done digital communication? You can proudly raise your hand. I'm not asking any difficult questions. Digital communication, yes, no. I've done. Delta modulation, what do we do? Okay, fine. I don't want to embarrass. Okay, in all those cases, what we say is that if you oversample something, let's say you have a smooth signal, you oversample it, you can always predict what will happen in future from all the past samples. Yes? Yes or no? Can we do that? If you have a very smooth signal, okay, and you sample a lot, then you can always predict what will happen in future from given number of past samples. Is that true? Yes? Your signal is not changing drastically. Okay, let's say you went to a very slow, boring movie and you slept. You're waking up every 15-20 minutes and watching a scene. And after come out of the movie theater after 2.5 hours, whatnot. Can you predict what happened in the movie? Yes or no? Slowly varying movie. compared to a high action movie and all. Yes. So slowly varying things are there or smoothly varying things are there. You oversample, you can always predict what will happen. And the same principle is used in delta modulation and all. Yes. So what they do is that typically they'll follow these kind of block diagrams. You have signal f of t. Okay. You can always predict what will happen in the future. And that prediction is nothing but your z of t. Okay. Let's say my prediction is very good. What can we say about the difference? Will the difference will be very small? That's the error, right? So the dynamic range of the difference would be much smaller. Okay. So instead of quantizing the signal, sampling and quantizing, can I sample and quantize the difference itself? Then I need a fewer bits. And that's what we do in delta modulation, where everything is quantized using only one bit, staircase approximation and everything. But everywhere we do a lot of oversampling. So how these two things are related? So right now there is no clear-cut comparison or study, except for a few papers like these and all, which talk about some pros and cons of all this delta modulation and other schemes and what is happening in unlimited sampling. And a good review or comparison of these kind of things would be very much useful in these kind of communities and all. Okay, fine. So why are we doing all this oversampling and everything? What is the reason? We asked a question, can we sample high dynamic range signal using low dynamic ranges ADC? Modulo, we can do that. Why should we do oversampling? What's the reason why you're doing oversampling? Yeah, to reconstruct essentially that operation called unfolding, right? You folded some samples, you want to get back like this, what we have done here, right? You have only folded version, you want to get back. Now, is it always necessary to do unfolding? Can't we do some job based on the folded samples itself? If we can do that, what will happen? Can we avoid oversampling altogether? Okay, I'll just give you one example. This is a speech signal, right? What rate do we sample the speech signal in general? Huh? 16K, 16K higher or whatnot, right? Now, why want to sample at 16K if you want to recreate it, right? But I'm saying that I don't want to recreate. I just want to know whether it's a female speaker or male speaker. Should we sample at such a higher rate? Should we quantize it at a higher rate? If the job is not to recreate, but to get some information from the speech. Okay, we need not have those many quantization bits also, right? So the same principle is what we are going to show is that in some application, you need not do any kind of unfolding, and with the folded things in some specific applications, you can solve your problem. Okay, fine. So I'll take you to a completely different field here, is the communication problem. So how many of you are aware of these kind of things, at least this picture? Okay, what we are doing is that I have 3 pulses, right? I'm transmitting more pulses every t seconds. Okay, and these pulses have a nice nature that they won't cause any disturbance at these points at t, 2t, 3t, 4t and all. And every pulse will have some amplitude A1, A2, A3, A4 and all. They are my information carrying amplitudes. Okay, so this is what we typically do in digital communication systems. I have some information that I want to transmit. I put that information in this amplitudes A1, A2, A3 and design these pulses. So this is more like a digital to analog conversion kind of thing. And this analog signal is what transmitted over something. Okay, and the receiver, what I do, I want to detect these symbols A1, A2, A3 and all, right? So what I do is that I just sample at this point and I'll get A1. I sample at this point, I'll get A2 and then A3. That's a simple detection that we do. Okay, simple detection. And what is the rate at which we do symbol detection? 1 by t, right? Because every t seconds I'm sampling. Will there be noise? Yes. What do we do in the noise, presence of noise? Of course, I will not have value A1, but A1 plus some noise, A2 plus some noise, right? If I assume that all these A1, A2, A3 are very far from each other, then I can do some sort of maximum likelihood and still find A1, A2, A3. Is that fine? That's what we do in generally. Okay. Now look at the dynamic range of this thing. This is huge, right? All this processing that I'm talking about, Of course, they have to go through a analog to digital converter, and then we do all the sampling and everything, right? What if the dynamic range of ADC is still very small, the way we thought about? Okay, we will have some sort of a folding here, right? So look at these signals. Sorry for the messy picture, but we have folded signals right now. And instead of having original samples, we have these folded samples. Yes? Is it fine? Anyone has any question they can raise? I can explain. Okay, so this problem was considered in some recent papers for MIMO communication and all those scenarios. And what they said is that instead of sampling at the symbol rate, of course, most of these signals are again band limited. Okay, and then you oversample, do the unfolding using one of these algorithms that we talked about, and then use your symbol detection. Okay, can we do that? Yes, no? Okay, again, all these signals that we are talking about generally are band limited. So you can use same principle that we had talked about earlier. You can do a lot of oversampling. You can do then unfolding, and then you can do conventional symbol detection. So we started having a question, should we do this oversampling, unfolding? All the oversampling and all we are doing just to do unfolding. Okay, can't we just use detection in that case directly from the folded samples? Okay, and this will usually result in much higher quantization error and all, because let's assume that when you are doing unfolding, you are applying some algorithm, right? If there is any issue in the algorithm, any error, it will carry forward to your detection as well. So we will want to completely avoid these things. So we started having question, what will happen if we can avoid the unfolding part completely? Okay, I'll just explain you this in a very simple sense. Let's say we have two-ary PAM signal. What is PAM stands for? Pulse amplitude modulation. Okay, you have four symbols. Okay, A1, A2, A3, A4, and all those things can take any of these four values. Okay, let's make a constellation. The symbols can take a value from plus C to minus C. And here are those four symbols. They're all far from each other, right? Your signals can take any of those four values. Your ADC's dynamic range is this. Is that fine? Okay. If I look at the folded versions of these AKs, okay, they may look like this. There's a possibility, right? After folding, they may fall on each other. Okay. Can I detect now? Can I do a detection? Because two symbols can fall on each other after folding. And I'm saying that I'm not going to do unfolding. I want to detect everything from the folded samples. Of course, two things are falling from each other or more things are falling on each other. I cannot do any sort of a detection. So there is no detection here. But what if the constellation is designed in such a way that for a given lambda, they're falling like this? Can we detect in this case? Yes? Okay. Now, as I earlier said, these are your symbols. Their detection ability is better if they are far from each other. Okay? Because let's say this symbol is there and a lot of noise around. If whatever you detect, it's falling somewhere here, you know that this is nothing but this. But here, can we have high noise robustness? Because they are now close to each other. Okay? Now let's at a simple scenario where we are having only quantization noise. Okay, fine. So we have a huge dynamic range ADC first, and now we have a small dynamic range ADC. What can we say about the quantization noise? Will it be same, higher or lower in our case after folding? After folding. After folding, of course, we are using lower dynamic range. We can have a lower quantization error. Okay. So in terms of quantization error and all, the noise will be much smaller in this case compared to this case. Even though distance becomes smaller, the noise also becomes smaller proportionally. So in terms of whatever the metrics are there, let's say symbol detection error and all, we will not be losing anything if we do the detection directly from the unfolded samples. Okay, that's what I mentioned here. Now, if I want to just summarize things in terms of bit error detection accuracy and all, I have three methods. One is the conventional one where we have a high dynamic range ADC and conventional detection and all that will always do well. So I have three SNRs, 10, 20, and 25, and I quantize everything after sampling into bits, 3 bits and 6 bits, two different scenarios. Then I applied one of the unfolding algorithm. As I said, unfolding algorithm will always have error even with a huge amount of oversampling. Here, I think we did oversampling by amount of 40 or something. Okay. So even whatever the error will be there, that will carry forward. And here we try to detect everything from the wrapped symbols. Now look at the scenarios when SNR is very good and we have a good number of bits. So you see this is performing as close as to the conventional methods. And this method is far better compared to unfolding methods, which requires huge amount of oversampling, but still they may give you some error. So one of the takeaways here is that in some applications, you need not do any oversampling and unfolding. So whatever the issues with the oversampling, like we can increase the power consumption and all, they can be avoided. Okay, fine. So it's end of the talk, the last slide. So in conclusion, what we understood here is that if you look at the ADC's power consumption, we cannot ignore. We all are using ADCs in some or other way. So we should focus on these things. Okay. And reducing the sampling rate, number of bits, and the dynamic range are all very key and important aspects. So whenever next time you work on any problem, you should focus on these things as well. Okay. Modular folding can be used to represent high dynamic range data using low dynamic range or fewer bits. That's one of the solutions. Okay. Sometimes unfolding may not be very efficient because it requires high oversampling and all. However, it can be avoided in some specific things where you need not have full reconstruction, but you're trying to capture some important information about the signal. Okay. And of course, many people might be interested. Deep learning methods have been developed and people are using these kind of things using deep learning. But there is some success, but a lot of scope to improve. Okay. Yeah. With this, I'll stop. If you have any questions, I can answer. We can use unfolding there. People are investigating that. Okay, but still we don't have too many results. But couple of ICAS back, there are some papers in the radar context where the signal consists of both very strong signal or strong interference and very weak signal. And they showed that using modular folding and all, they are able to detect a weak signal. But there should be strong characterization of that interference and weak signal, some sort of separation and all. Yeah. Why not? Okay, great. Yes. Yeah, it all depends on how much oversampling you want to do. You always have smooth signals. You are modulating everything to ISI pulses or and all. It will always work because most of the signal that we will be dealing with in COM and all are band limited signals. And whenever there are band limited signal, you can always oversample and make them like near correlation and all. Those assumptions will always be valid. I didn't get the question. Can they unmute and ask maybe?
Hello, sir. Am I audible?
Meanwhile, for all of you, I just pause 1 second. Yeah. This is a JTG summer school that happens every year in one of the IITs and all. Next year, it will be in IIT Bombay, and these are the speakers. This is a 5-day event with these tutorials and everything. The registrations are open. You all can register. The links are also given. Yes.
Sir, am I audible?
Okay, next question maybe. Should I unmute myself?
Hello, am I audible?
Yeah, Soham.
Yeah, am I audible?
Yes.
Okay, great. So thank you for the talk. I have a couple of questions. So the
Yes,
first
please.
question is basically, will the assumption of this nearby value that you had assumed, right? So will it work for signals like OFDM where we are using 64 or 256 QAM kind of modulation on each of the subcarriers because they have a very high PAPR? And the second one is what about the signals where we are trying to detect any event where a spike will appear in the time domain signal? So do you think this technique will work in those scenarios?
Okay, so if first for, I think there is an echo. Should I mute myself here and answer you? Uh, can you hear me now, right?
Yeah, I'm able to hear you, sir.
Okay, see, I muted you, sorry. So for OFDM signal and all, see, irrespective of how much COM you use, you always modulate them to a pulse, which is band limited. Either you use raise cosine or sync pulses or something. And all we are looking at the final signal here, most of the conventional methods. So if the signals are band limited, you can always have oversampling rate such that this near sample smaller, the difference between near sample smaller than some threshold will always work. And maybe I'll unmute you for your next question. Can you ask your next question?
Yeah, sure. So the next question was basically, what about those signals where we are trying to detect any event where they will appear as a spike in the time domain waveform?
Yeah. So these are not band limited signals. There are a slightly different kind of signals. So few works are there or something called a finite rate of innovation signals and all, which are stream of some spikes and all. So in these cases, what we do is that we first pass these kind of signals through a low pass filter or some specific filters, make them smooth. And this or some other kind of methods are there. This is one of the methods that I talked about. There are several others which use for the reconstruction of those spike locations and other events and all in these cases, but not directly these algorithm. That algorithm that I'm just showing or mentioned are for band limited signal of a few specific cases, but there are a number of other algorithms.
Uh, Sure. Thank you, sir. And the last question, sir, what is
Yeah.
the hardware behind that modulo folding block? Like, since this block is before the ADC, right? So I believe it's an analog block. So how much
Yes.
power does this modulo block actually consume, and how significant is it compared to the power consumption of the ADC?
Uh, that's a great question. So we haven't answered that. Yeah, we haven't answered that in that particular paper, but there is a recent paper in Signal Processing Magazine or which will appear where we compared what should be the power consumption of this folding block compared to the ADCs. And when can we say that together they are much more efficient? This, what are the prototype I showed, we haven't answered those questions there. We just want to show that the folding can be done in an analog domain.
Okay, sir. Thank you so much.
Yeah. 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 Anyone can ask questions. Yeah. Okay. Anyone else in the audience? In the digital domain. Okay. That's the thing. See, modulo sampling, when you look at modulo, so folded signal, you can always write it as a linear combination of original samples plus some residue. Now, how you treat your residue, whether the filtering is used